morning, everybody. Welcome to the Hudson River Foundation to our fall Edward A. Ames Seminar Series. We're a little out of whack. This is usually our first Tuesday seminar, and you notice that it's not the first Tuesday, it's not even the first Monday, but it is October 24th, and we're pleased to have with us Helen Bailey from the Chesapeake Biological Lab, part of the University of Maryland. Just to give a little bit of background before I introduce Helen. We have, for those that are on the webinar, we have about 15 people here in our office. I think there's about 20 of you online. For those of you that have participated before, you will know that, or hopefully you can hear us and you can see us, what we're doing, and we hope you're going to interact with our speaker later on. We ask you just to hold questions. You won't be able to speak to us, but you have the opportunity online to write some questions, and we'll do our best, and Helen will do her best to address them later on. I just wanted to also mention that we have another seminar next Friday, in a week from Friday. Bob Howard is going to talk about nutrients and the impact of climate change on nutrient impacts and effects. So that again is on a Friday, so it's we're a little bit out of whack with the Tuesday schedule. Okay, so technology is wonderful. Technology is great, and fishery biologists are using technology more and more. Unfortunately, technology is coming to the Hudson River estuary and the study of some of our favorite anadromous species like striped bass. A few years ago, David Secor from the University of Maryland David has been conducting work on striped bass and other species for quite some time here in the Hudson. As part of his continuing work on looking at the migration of striped bass, he tagged a number of fish. I think there were 75 fish back in about 5 or 6 years ago. And he was testing his theories on where striped bass go and these different contingents and so forth. And I think some of you in the room may have heard him speak last year about his work. Well, combining that data with other sorts of data, I guess we'll hear from Helen that you get lots and lots of data. You can track individual fish, where they go, where they've been. It just so happens, too, that the work that David did included time frames when we had our favorite events, in particular Hurricane Irene and Lee, that we know added tremendous amounts of fresh water to some of our tributaries here within the Hudson. And we have an opportunity now to take a look at potential impacts of those events on one of our favorite species. So we're pleased. We were thrilled that Helen submitted a proposal to us. It was going to look and drill down into that data set and tell us more about what fish are actually doing on an almost moment-by-moment basis when faced with these extreme events. So Helen got her PhD from the University of Aberdeen in the UK several years ago, and now she's a research associate professor at Chesapeake Biological Lab, and we're thrilled to have her here. Helen.
Thank you so much. It's great to be here. And I do want to say a big thank you to David Secor. It was really sort of our over tea coffee discussions that we came up with this idea, because I do have to confess that I am not a traditional fisheries biologist. When I was at the University of Aberdeen, there we go. So this is what I was studying up in Aberdeen, bottlenose dolphins in the Murray Firth, which is in the northeast of Scotland. And I was actually studying their movements by standing on land with a theodolite, which is a surveyor's tool. You may have sometimes seen them by the road, but essentially they measure horizontal and vertical angles extremely accurately, which when you know your height above sea level, then means you can get very accurate positions of an object. And in this case, we were tracking bottlenose dolphins, and so they come very close to shore, and given the topography there, we could actually track the animals as thick from land. I then moved to California to do a National Research Council postdoc at NOAA, and there I was working on whales and also sea turtles. And I've worked on a number of different species, and the common thread there is that it's, as I say, this analysis of movement, looking at how the animals are moving, how are they influenced by the environment, how are they responding to the environment. And that's where, having talked today, we thought that maybe some of those approaches could be used on striped bass. So I'm going to talk a little bit first explaining what I mean by movement ecology. This is a relatively new field, but with the tremendous amount of data that we are now collecting on animal movement, and particularly this explosion in our understanding of marine animal movement, this is really taking off. And I'm going to talk a bit about the methods that I've used for analyzing animal tracks from satellite telemetry, and then how we applied some of those techniques to acoustic telemetry, and more specifically to look at the response of striped bass to extreme weather events with two storms in 2011, tropical storms Irene and Lee. So first of all, when we think about animal movements, and I was just hearing a little bit about the striped bass tagging program, and this is essentially the type of information we often get. We have a starting position and an ending position, and we could assume, for example, that the animal has moved between those 2 points, and we can assume it's just linear. Or given the shape, for example, if it's in a river or they're influenced by currents, we might see slightly different deviations from that straight line pattern. We might see that there had been movement back and forth. We might see that actually there wasn't straight movement at all, that it's relatively convoluted. Perhaps they're searching for food or some type of other resource, whether it might be for breeding, raising young. And as the time between these 2 points increases, you get this sort of increasing uncertainty in where the animal might have been. Now, the more traditional method for looking at particularly fish might have been to do surveys, sample certain areas, and we can look at the abundance at different sites. And I've indicated, for example, here, just in this little schematic, that abundance could be the increasing size of the circle. But if we look at the other panel, I've drawn the movements that could potentially have led to this pattern. We can see that by looking at animal movements, we can get a much better understanding of not just, there are certain areas like these red dots, these are high abundance, and we have the orange and medium abundance, and then lower abundance in the yellow circles. But actually, there might be different things going on. So there might be movement in one direction in one area. We might have back and forth movement in another. We might have some sort of foraging in the center here, leading to high abundance, so lots of animals are feeding. So lots of different behaviors can lead to these type of abundance patterns. And I'm just going to show an example here. This is a sea turtle. This is actually a leatherback turtle, the largest species of sea turtle. They can grow to over 7 feet long. And here we have female turtles tagged with satellite transmitters leaving a nesting beach in Costa Rica and moving southwest into the South Pacific. And each dot there is a day, it's a mean daily position. And I'm showing you 120 days here, so about 4 months. And you can see if we look at this sort of polygon, they span quite a large area in those 4 months. I mean, if we look at the latitude here, they're spanning hundreds of miles. But when you saw that movement, you could see that it was relatively synchronized. They were following a certain pattern. And so at a given time, the area they're occupying was actually much smaller. Now, as another example, I have a fin whale here. And in July of one year, we have the green star, and the following year, almost the same time, the next year, it was seen in almost the same location. So if you think back to my first diagram, if we had just drawn a straight line, we would have said it had gone very little distance at all. It had just stayed in that same place. But we actually had a satellite transmitter on this animal. And we can see here, I've got each day's position as a dot, and I've got it colored now by sea surface temperature. Now, the paradigm for large whales is they go to warm tropical waters in the winter, usually to breed, and then cooler, temperate waters to feed. This whale decided to go right up to the Gulf of Alaska for the winter. It's in waters 2 to 4 degrees Celsius, so just above freezing. And then it goes all the way down south to just below 20 degrees north. This is in April. It then returns back up to the Gulf of Alaska and then back down south to Southern California for the next July. So it's really exciting to see that even with an animal that we thought we had, we clearly understood their migration patterns, we see these exceptions. And what we want to learn now is this an exception to the rule? Or is this actually what the whales are now doing? Is this a response to changing climates and prey distribution? Or is this that actually our data, a lot of which from the past was from whaling, is just not accurate anymore? The oceans are changing, they're doing different things. Maybe it wasn't giving us a full picture. So certainly my impression is the more we learn about animal movements, the more we realize we have to learn. So I find it very exciting, and I say with the striped bass, that was really exciting too. So movement ecology has been defined as understanding the causes, mechanisms, patterns, and consequences of movement phenomena. So not just showing you pretty map saying the animal went from A to B, but trying to understand why it was doing that, what was causing that. And then we can link movements to specific functional behaviors. So, for example, the animal's feeding, breeding. And I have a little picture here showing different scales. So we have from the smaller scale, the individual, what we call sort of movement steps, going to movement phases. So these are now sequence of steps that form a specific functional behavior. So we have this convoluted pattern here that might be searching for food. And then we have the straighter movement here, which is, given an example, escaping a predator, or it might be transiting between food patches, or it could be migrating. And then we have at the larger scale, the lifetime track. And for many animals, we do not have a lifetime track. Many of the animals that I've studied live many decades, and we do not have a tag that's been able to track them that long. But certainly that obviously will be going to the goal, is actually understanding the full life history of an animal. Now, I'll talk a little bit more now about, well, why do we want to be studying individual movements? A lot of the interest from population ecology, community ecology, and from management is more on the population level. And I would argue that in movement ecology, even though the focus is on individual animals, we're trying to use that to understand patterns of population dispersal. And as certainly as our data sets increase, as we get bigger sample sizes, then we can start to see how that is representative of the population. And the advantage is that movement incorporates both the spatial and temporal dynamics. So we're not just getting a survey that's just giving us a snapshot for a short period of time. Hopefully, as we get these tags that will last several years, for example, the tags in the striped bass that were lasting about 2 years, then we can see how the movements are progressing on a seasonal and annual scale. And then we can make inferences about the behavior and then start to assess fine scale responses to events. And so that's the real focus, looking in our case at the response of striped bass to these extreme weather events. Now, I've mentioned acoustic telemetry, I've mentioned satellite telemetry. I thought I'd just give you a little more information in case there were those who weren't very familiar with tracking technology. So these are the 3 main tracking technologies that have been used with global coverage. We have geolocation, which is using usually light levels, but it can also use sea surface temperature, depth sensors to try and reduce the error, but generally these have the largest uncertainty in the location. We then have Argos satellite, which has on the order of 1 to 10 kilometers error, but has been widely used on air-breathing species. The animal does have to come to the surface, or at least the tag has to come to the surface in order for it to transmit to the satellite and obtain a location. But it's been widely used on many large marine species. And then we also have the GPS, which has even finer resolution, really high accuracy. And then we have the acoustic telemetry, which generally requires either for you to be following the animal in a boat, the mobile tracking, or mooring receivers to the seabed. And then we have fixed locations. So I'm going to talk first a little bit more about the work I've done to do with satellite telemetry and the techniques we've been using there, and then I'll move on to the acoustic telemetry and the straight back. So for satellite tracking, we tag the animal usually somewhere on the back or dorsal fin, so that when the animal comes to the surface, usually there's a saltwater switch on the tag, it gets switched on, it emits a radio signal to a satellite overhead, and based on the Doppler shift in that signal, a location is estimated and it's processed on land, and then that information is sent to the tag owner, so that they'll receive a sequence of locations, latitude, longitude positions with the time and date. Now, I was lucky when I moved to California, I was working with NOAA to be working on the Tagging of Pacific Predators project. This was a 10-year project that was part of the Census of Marine Life, and they tagged 23 different species, which range from seabirds, fish which included tuna and sharks, they had sea turtles, marine mammals, from whales to seals and sea lions. And when I joined the project, it was actually in phase 3. So during phase 1 and 2, they had been doing tag development and a lot of tagging. And you can see, I mean, it's a data deluge, a tremendous amount of data they had collected. On those 23 species, they had thousands of positions. And so I came in to help analyze this data. And as a first step, when you're trying to deal with data sets this size, we thought we'll start by breaking it up into different gills, different groups. So we've got the tunas, we've got the seals, we've got the sharks, the seabirds, the turtles, and then the whales. And I'm going to talk a little bit more about the whale data set. And I'm going to focus on the blue whale, which is the largest whale species and the largest animal on the planet. It can be up to 30 meters long. Its heart can be the size of a small car, and some of its blood vessels are so large that someone small like me could swim through them. So this is an incredibly large animal, but interestingly, it actually feeds on a very small animal. It's a specialist on krill. So it's a filter feeder. It's a baleen whale. It has baleen plates to feed, and it feeds on very dense aggregations of these krill. Now, although whaling is no longer allowed in U.S. waters and hasn't been for some time, whale populations were severely reduced by whaling, and now we are seeing some recovery. We have good news with the humpback whale. Many of the populations have recently been taken off the endangered species list. They're now listed as just threatened. The gray whale has come off the list entirely. In fact, they think it's now reached carrying capacity. So we do have some good news stories with the whales, but unfortunately with blue whales, their numbers have not been recovering as well. In fact, many of the populations still seem to be stable despite being protected. And unfortunately, their biggest threat is still humans. We have entanglements in fishing gear, we have collisions with ships, and we also have loud underwater sounds. And for the blue whales, the biggest concern has been this collision with ships. Off California, or off the U.S. West Coast, they've determined that they think only 3 whales can be killed by humans for it still to be sustainable for the population. And in some years, such as 2007, there were 4 whales hit by ships off LA within about a month. It's just very unfortunate that year there were a very large number of blue whales feeding right in the shipping lane. And I should add that the number that is reported is probably a very big underestimate of the actual number that hit, because the ships are so large, they might not know if they've hit a whale, and if a whale is killed, their bodies might sink to the bottom. So it's only confirmed cases that we have reported, and it's probably much larger than that, the real number. So I was working with Bruce Nate and his team at Oregon State University, and they've been tagging whales for a large number of years. And for the blue whales, it had been over a 15-year period where they had tagged 171 whales over that time frame. Most of the whales were tagged off California during the summer and autumn. And their method had improved over time. So we had in the early years some relatively short tracks. Some of the tags transmitted for less than a day, but as time went on, the tracking durations became much longer, and many whales were tracked for many months, up to a year, and the highest number was actually 504 days. So we had a tremendous tracking data set for these blue whales. And here's an image showing you these tracks, and the different colors represent the different sites at which they were tagged. Most of them were tagged in Southern California and Central California. But despite where they were tagged, we see the same general pattern of their movement, mainly along off the coast of Mexico and the U.S. West Coast. Most of them go south in the winter into the eastern tropical Pacific, with some going into the Gulf of California. Now, as a movement ecologist, I go through a process which I said this is actually named by Dave, that we reduce, we reconstitute, and then we predict. So what does that mean? What are we doing? Well, what we do is, first of all, look at the movement patterns. I mentioned earlier about looking at movement steps. So for the Argos satellite data, given the frequency with which we get positions and the accuracy of those locations, we usually look at about a daily time scale. And what I'll do is, from that, I will look at the speeds of the animals, I'll look at the turning angles, and I'll look at the autocorrelation in the speed and direction. And here I've just done a little cartoon to indicate. We imagine, for example, the stars, there are locations, and we've got movements between them. So we're calculating these different metrics. And when animals are foraging, we assume that they're going to try and stay in a patch. For example, today, these blue whales are feeding on dense aggregations of krill, so they're going to generally have slower speeds, they're staying in the same area, high turning angles, low autocorrelation in speed and direction. Whereas migration, we see the converse, where they tend to have much more directed movement, higher speeds, much higher autocorrelation in speed and direction. So we can sort of partition different behaviors using these metrics. But I mentioned that Argos satellite data can have 1 to 10 kilometers error. And so when we calculate these things, essentially we've got that error still in the position. So more recently, we've been applying something called state space models. These are used in a variety of different fields. It's a very broad term, but essentially it's a time series model that predicts the future state of a system from its previous state probabilistically. And what do I mean by that? Well, I've just done this cartoon so that indicate, for example, if these yellow stars connected by the black lines were our Argos satellite positions, you can see we've got a position over here that maybe looks a little suspicious. Now, we will have an indication of what the error around this position might be. We also have from the movement of the animal previously. For example, if it was moving in a very straight line, it's fairly unlikely it suddenly deviated and then went back to that. So if this has a relatively large error, and given the movement pattern we've seen in the past, we can give a best estimate of where we think the animal actually was. So the state space model has 2 components. It has the measurement equation, which is taking into account the error in the location to sort of give where could the animal have been. And then we have the transition equation, which is that movement aspect, where given the animal's behavior, what we would expect it to do next. And here I've got an example here of more foraging type behavior versus transiting behavior. So I applied this model to the blue whale tracks, and we can see in red here, these are the foraging type behavior. I've actually called it area restricted search because we see that localized movement when the animals are breeding as well. So we've got our foraging grounds, and then we have what we think are our wintering breeding grounds. Now, if we look at that in a little more detail, we can see now I've got parts of individual tracks here, and you can see their movements as they're zipping around. And some of them are quite tight, they're staying in a very localized area, and some of them are just a little more spread out. So another question I had, well, how big are these patches? Now, I don't have estimates of the krill for all the times and locations of the whales, but I can look at the whale behavior to get an indication of what scale they're feeding at. And here I use a technique called first passage time. This is a relatively simple concept of the time it would take an animal to cross a circle of a given size. And we can look at that at various different circle sizes. And when we see it transitioning from relatively straight movement to high convoluted movement, then we see this sudden change from a relatively fast first passage time to a slower first passage time. And so that change then gives us an indication of the scale. So I've got here, we look at the variance against of first passage time against the first passage time size. And here we can see there's a relative amount of variability, but the peak was at about 50 kilometers. So we're still talking about relatively large areas, but we're also talking about a very large whale. But when I looked at it across years, we see this very large variability in that patch size between years. And I think that's just a difference between individuals, that some individuals are focusing on very small patches, and then they move on to another one once that's depleted, whereas others are sticking around in the area. So there was no significant difference between years. There was very high variability. So it was very interesting to look at that foraging behavior of the whales. But as I mentioned, there was also a very distinct seasonal pattern where the whales were off the US West Coast in the autumn, and then they start heading south in the winter, and then they're heading into this eastern tropical Pacific, and then in the spring they start moving north again off Mexico, and then into the summer they're off southern and central California. So what we wanted to know is, okay, we don't have krill data, but krill are strongly affected by things like temperature, the water depth. They tend to aggregate at the edge of the slope. Could we use environmental information as proxies for the krill to predict the distribution of blue whales and capture this seasonal pattern? So that's what we did, is we combined the whale positions with environmental data, various different environmental variables, say from static ones such as depth to more dynamic ones such as sea surface temperature, chlorophyll concentration is an indicator of productivity. And then we had sightings data from boat-based surveys that we used to validate our predictions. And then we actually automated our model to create a near real-time tool. So I'll just show you, so here I've shown you for each month sort of representing the different seasons, predictions that we had for 2009, which we used as a test year. So we have in the spring here, they're starting to move up into Southern California. We see much higher occurrence into July, but then all along the US West Coast in September, and then they start moving south again in December. And I'm just going to show you a little video now. Here it's going month by month. So here we've got from January through into spring, heading up north. They're moving up along the coast. You get these high occurrences, high densities, and then the densities go down as they move back down south again. So having used 2009 as our test year, we were excited to see that using these environmental variables, we could capture this seasonal pattern. And working very closely with NOAA and the NOAA West Coast region, we have our product now up on the NOAA website. So if you Google NOAA Whale Watch, you can come up with this page. And this map is updated every month. So what's happening behind the scenes is we've created this automated tool where it will extract the latest environmental data for sea surface temperature, chlorophyll concentration, sea surface height variables that were found to be important, together with the depth and slope information. It's then run through our habitat model in which we've established this relationship between the whales and the environment. and then it outputs the predicted values on these maps. And we've also tried to capture sort of our uncertainty in these by giving not only our average prediction, but lower and upper, so you can sort of see the range as well. Okay, this gets updated every month, and then we have an archive page where previous months' maps can be viewed. And you might think, well, why do we need the current month's prediction? Why can't we just use an average prediction for September, for example? And here is an example where we've got the September prediction for 2009 and then 2015. And you can see just how different they are, and that's because the environment was different. And that's what NOAA has been struggling with, because they can impose vessel speed restrictions. So they can ask the boats to slow down, and the idea is then it's less likely to be lethal to a whale. But how do they know when to impose that? Because there's strong opposition from the shipping companies. They don't want to slow down. It means they take more time. It means money. And some years there's no whale strike, so why should they have to slow down every year? So using these types of tools, we can help give information to NOAA for them to make that decision. Is this the year that they should be imposing that vessel speed restriction or not? And even off Central California, off San Francisco Bay, there are 3 different shipping lanes. So there they could even make a decision of this month, do they potentially want to close one of the shipping lanes because there's a really big aggregation of whales. And so it might be better if the ships use the more southern lane, for example. So this is helping them make these types of decisions with an understanding that we know there's interannual variation and that the whales are affected by the environment and their prey. And this leads into the concept of this dynamic ocean management, that we don't necessarily need static areas all the time. Obviously, with fisheries, there's been time area closures for some time. But say the idea here is just taking that almost one step further, where it's not just one area that's sort of on-off, but that area can move. And particularly as we move further offshore, where we don't have land and bathymetric features necessarily bounding it, we can potentially have areas that are moving with sea surface temperature, ocean fronts, that animals are following, and we can help to show where those are and how they're moving. And the idea is that this means an area doesn't have to be closed all year round. It might be just certain area for this month, and then they move to the other area. Like I showed you with the leatherback turtles, this migration, sometimes if we see that movement, it just means you don't need to close an area for a very long time period. So it's trying to take into account that there are human activities. We're not going to get rid of every human activity, and trying to see if there are solutions to reduce human activity and wildlife conflicts. And just to mention, if you Google it again, that eCatch app, it does exist if you want to take a look at that, and that's trying to reduce bycatch in the California drift gillnet fishery. So we've had the whale talk. Let's move back to fish again. So now with acoustic telemetry, it just works a little bit differently. So we have a tag that is either attached onto an animal or inside an animal. And the advantage with acoustic tags is they can be a lot smaller than the satellite tags, so we can put them in smaller animals. And I say we can then follow them, for example, in a boat using a hydrophone with mobile tracking, or we can have fixed receiver sites. And here I've got an example. So where you have an area with the river and the harbor here, we can have sort of a gate design where we're putting them at entry and exit points, so we know when our tagged animals are moving through those areas. That's a little bit trickier when you get to the open ocean, but in these coastal environments, it works very well. And we are getting an incredible network of acoustic receivers. This really is a tremendous time for acoustic telemetry, and there's been wonderful cooperation between different scientists and groups to share information, because there's obviously people who have tagged animals that maybe go past receivers owned by other people, and that data can be shared, and the Atlantic Cooperative Network has really played a strong role in that. So as mentioned in the introduction, David Secor at the Chesapeake Biological Lab tagged 75 striped bass in October 2009 and May 2010. And many of you may also be familiar with the contingent idea, but just briefly, they've identified 3 main contingents the upper estuary contingent that mainly stays in the Hudson River and stays up there spring, summer. There's some movement down the river towards the winter, but they don't tend to move further than that. We then have the lower estuary contingent. Those animals go obviously up to the river to spawn, but then move back down to the lower river and the New York Harbor area for the summer, autumn, and sometimes into the coastal environment in the winter. And then we have the ocean contingent, which again come up the river to spawn, but then tend to move back out into the coastal environment. So the ocean contingent tends to spend the least amount of time in the Hudson River estuary. Now, incredibly, some of these tags lasted up to 816 days. And I think when Dave tagged the animals, he was hoping they would last at least a year, maybe 2 years. I'd say some of them lasted even much longer than that. And I have a video that was made by Dave and his assistant. Hopefully show. It wasn't actually filmed in the Hudson River, but gives an impression of the tagging process that I thought might be interesting to see. We have real-time footage here. Hard work being scientists. So I thank obviously Dave for all his work with the tagging, and it does take quite a bit of work, but as we'll see, it is really amazing the information that we can collect by looking at these movements and the finer scale information that we can gather. Now I've just got a little video here, which hopefully will work, that just shows for a few months some of the movements of these striped bass, and they're colored by the different contingents. So we've got the upper estuary contingent in red, the lower estuary contingent in green, and the ocean contingent in blue. And what you'll see is, so these little fish popped up when a detection was made at a receiver. So you can sort of see as we head into the spring, they're going upriver, and then we start seeing movement back down again, and some of the fish will go out the coastal environment, and some are heading down into the harbor. And generally, the way that a lot of people have been thinking of this acoustic telemetry is to look at it on a receiver by receiver basis. To look at, for example, the receivers in the river and see when was their ping, when were their detections, and it's been a little bit more almost sort of thinking on it like with a survey, that you're in a location at a certain time and when were fish going past it. And with my background, having looked at satellite telemetry, I was more used to seeing these individual tracks. So that was the way that I approached it. And I say, what I think they didn't anticipate when he tagged these striped bass was just how many detections he was going to get. We have over 550,000 detections of these 75 striped bass. So you can see just how amazing in terms of understanding their movement, even though we don't have complete coverage by any means once they reach the coastal environment. A lot of the fish are spending a lot of time in the estuary where we do have good receiver coverage, and then even as they move into the coast, we'll be getting a lot of detection, particularly as even now there's even more receivers popping up related to other projects. But with the work that I was doing, I wanted to look at their individual movements, and I was focusing really on the sort of lower estuary New York Harbor area. And I've just got this little animation here. So here we have a fish. It moved down the river, moved down into the harbor, hung around there, and then it went to the end. And I'll just show you that one more time. So it was a little bit quick. So if we go back to this is IV11. This is a lower estuary contingent fish in May. So after spawning, it's come down the river. It's been detected there. Goes down, we get detected Kilburn coal, hangs around there, and then in October we see it move out to the southern part of the harbour. And reconstructing these movements, essentially that's what I've done here. So here we've got movements of a fish moving down the river, goes up here, goes down here. And what I essentially did is construct all these little diagrams for all the fish that they had been tagging, looking at their movements. And it was really interesting because, I mean, like with the whales, there's a relatively predictable seasonal pattern to their movement. So having understood that there is this relatively predictable seasonal pattern, the hope was if something happens, like an extreme weather event, would we be able to see a deviation from that seasonal pattern that we predict? Now, unfortunately, with climate change occurring, they've predicted that extreme events are likely to increase in intensity and frequency. So although we might consider a storm a rare event, in the future it may become less rare and even to the point of becoming the norm that we have at least 1 to 2 big storms every year. And depending on when they occur in the year, this could potentially have impacts on the population. But it's very difficult to study these phenomena because at the moment, by definition, storms tend to be rare, they tend to be unpredictable in their exact timing, and they tend to be rather undesirable times to be out there surveying. In fact, with the biweekly surveys they do, there was a number of surveys that weren't conducted during the period of storms, presumably because they were unsuitable conditions, it wasn't safe for people to be out there surveying, and the advantage with the acoustic telemetry is we could track these animals regardless of the fact that it wasn't safe for us to be out there. So we have this wonderful data set say that even though the animals were mostly tagged in 2009, went right through to the period of storms in 2011. So you're probably even more familiar with this than I am, but we had tropical storm Irene, which had been a hurricane, but as I said, as it came to landfall, was considered a tropical storm that hit at the end of August 2011, which was followed very shortly after by Tropical Storm Lee. So we had 2 events very close in time with very heavy rainfall, very large amounts of freshwater input, very high discharge rates. And for comparison, I put 2010, the same period in the previous year in gray. And when I looked at the previous 10 years, 2010 was actually very close to the average. So we're going to sort of consider 2010 a typical average normal year. And you can see that the pattern there, this is in water level, and we have these very strong peaks at and just after the storm events. We have a very rapid decline in water temperature. The freshwater input also causes a steep decline in salinity, and then we also had a decline in dissolved oxygen. This data is actually from sites in the lower estuary, from the USGS daily statistics and from the Hudson River observing system. And I do definitely want to say a huge thank you to the efforts that go into these observing systems to be able to have this environmental data to link with the animal movements is really critical. So obviously the environment changed very dramatically and rapidly that these fish were in. And so given that we knew from the seasonal pattern in August to September, we tend to see fish moving out to the harbor and into the coastal environment, or certainly some of them. anyway. So my concern was if I just looked before, during, after the storm, we might see a southward movement that really you could say, well, that's no different to any other year. So we want to be able to distinguish the typical seasonal pattern in their movements from what had been event-driven. So we did a before, during, after control impact design. So like before, with the 2 weeks before the storm, the 2 weeks during the storm, and the 2 weeks after the storm. And then as my control year, I have those periods for 2010, and then the impact year is 2011. So those periods for 2011. And my response variable is the mean daily latitude for each fish. So I wanted to capture their movement. And essentially, as you've seen in those maps, we have this sort of north-south movement. So I'm essentially using latitude as a way to look at that. And here I've just got, as an example, we've got latitude on the y-axis and we've got time on the x-axis. This spans from when they were tagged in September 2009. And you see this fish moves south, then into the spring it's moving north up the river, and then it moves south again in the summer, and then as I said, these pale red lines are the corresponding period in 2010, and the dark red lines show the actual timing of the storm event. So if you look at the year before, you can see, oh, they both have southward movement. But the key question is, was the southward movement significantly different in any way in 2011? So I fit a generalized linear mix model because we have autocorrelation in these movement patterns. So we have, as a random effect, the track sections within each year nested within the individual. Take that autocorrelation into account. So I've got as an example here, this is fish IV3, this is from the upper estuary contingent, and I show this as an example because it's even more dramatic because the fish is coming from further upriver. So we would expect the fish to be spending the summer in the river, and then they're usually in the lower estuary or the harbor during the winter, and that's exactly what this fish did in 2010. And then if we look at 2011, you can see here it is up in the river. The storm event detected, the first storm event occurs, and it actually is still detected in approximately the same location, but after the second event, you can see this rapid movement south. You can see just how steep that line is. And I've actually calculated the speeds here to illustrate that, where on average, the movement in 2010 during that time period was 0.02 meters per second, which for this fish, which was just under half a meter long, is about 0.04 body lengths per second, which is a relatively slow rate, but fairly typical when we're averaging it over these time frames. But you can see, I mean, the rate here is nearly 1.5 body lengths a second as it moves south from the river into the harbor. So very fast movement down. And what's interesting is even in this period after the storms, it keeps going. It doesn't just stay in the harbor, it goes right out into the coastal environment. But then it did come back. So we do see some movement back as well, and I'll mention that in a moment. So looking at the latitude of these fish, we saw that there was a significant interaction between the time period and the year. So even though it was typical of fish to move southward, there was a much more pronounced southward movement, significantly further south in the period after the storms in 2011 compared to the previous year, indicating that we were seeing this coastal evacuation of the fish. They were moving out into the coastal environment. Now, I repeated this analysis, and instead for the response variable, I looked at the residency time in New York Harbor. And to estimate that, I didn't just look at when fish were detected, but I also looked at when they were detected at one site entering New York Harbor to when they left, and assumed that during that time period, that meant they were in New York Harbor. As I say, since we had this gates design, it was well designed for me to know when they could be entering and leaving the harbor, so I don't just need to use the detections, I can actually look at the time period between the detections as well. Now, when I did it on that 2-week time scale, there was no significant difference. But having looked at all these individual movement patterns, what became clear to me is in August, September, we had some fish from the lower estuary in New York Harbor moving out, So we had some occurrence of fish in New York Harbor, but we also had, as I just showed you, some of those upper estuary contingent fish that obviously took longer to get down the river into the lower estuary and New York Harbor. So then I had a higher occurrence into the end of September. So that's why I wasn't seeing a significant difference in that before, during, after period when I was only looking on that 2-week time scale. But if I looked at a monthly time scale, then I saw that there was significantly lower occurrence in October compared to the other years. So essentially what we were seeing is that fish had moved out of the area into the coastal environment. So by October, we were seeing less time spent in New York Harbor than we would have expected in the previous year. So this changed, obviously, their movement patterns, their residency in New York Harbor. And this made me wonder, well, was this just such incredibly fast flows? These fish were getting flushed out. They were just getting washed out of the river and right out into the coastal environment. So what I wanted to do was look at, well, did any fish actually manage to stay in the river? And the answer is yes. There were 3 fish for which we had detections throughout the storm period, so we could see where they were throughout the storm, and 3 fish actually remained within the harbor throughout the storms and after them. And these fish ranged in length from, I think it was 490 millimeters, right up to nearest our largest sizes of over 700 millimeters. So it didn't seem to be size related. It wasn't just the biggest fish. We had a range of sizes, and I'm showing you just one of them here. This is the medium-sized one at 590 millimeters. So clearly they were able to stay, and that's despite the fact that we were estimating very high flow rates. So the discharges that had been measured on average in September, about 269 meters cubed per second, whereas there was a daily average recorded of over 4,000 during the storm. So incredibly high flows compared to the average, and we estimated that that could lead to speeds of 2 meters per second. And certainly for the smaller fish, that could be beyond their maximum sustainable speed. So presumably they're able to find refuges, and interestingly, where they're being detected here is out near Liberty Island and Governor's Island, so maybe they were able to find some kind of refuge from these fast flows. And able to maintain their position and stay in the area. So it isn't a case of just all striped bass being washed out. And as I mentioned, we also saw in some of the tags that transmitted long enough, some of the fish did stay out in the coastal environment. They did stay south, but other fish did return, and this was particularly in the upper estuary contingents. These are the fish that would normally winter up the river. It appeared they clearly wanted to go back there, and they did what we think these sort of exploratory trips, go back to the harbor, maybe checking the conditions, decided no, it's not good enough, went back out again, and then returned and continued up into the river. So in this example, it returned in late October. It was detected off Sandy Hook for a few days, and then returned a week later to New York Harbor, and then continued up the river. So we could say that based on this, then there wasn't a long-term impact of the events. The fish did return about a month later, or a bit over a month later. But as I mentioned, as storms become more frequent, as they occur at other times of year, for example, if we have storm events during spawning and these fish get moved out, that could potentially have much bigger impact on the population. So I think it's certainly something we want to think about for the future. Now, although we didn't have any acoustic telemetry data for white perch, we thought it might be worth just looking to see, well, were other species doing the same thing as the striped bass? And we thought white perch were a good example because they're an estuarine species, but they tend to be more abundant further up the river. It's rare for them to be abundant in this lower estuary area. So we looked at the survey data, and we see this very strong peak in battery and yonkers here in the lower estuary after the storms, and then it goes back down again. So it looks like white perch will also move down the river as a result of the storms. So in terms of next steps, within the project we have funded and also working right now and just completing actually developing a habitat model for striped bass in New York Harbor with the idea of the understanding that in associations with the environment could potentially be used for management. And also, as I mentioned, our network of receivers is really growing. This is a fantastic time to be studying these animals using acoustic telemetry. So also looking more at the coastal habitat use of striped bass. And we've been looking to I have a marine mammal project funded in the Maryland wind energy area. So this is offshore of Maryland, off Ocean City. There's a wind energy area been proposed about 10 to 23 miles offshore. And I had a project funded to put hydrophones out for whales. Now, we don't tag the whales, we can just hear their calls and detect them that way. So it's very non-invasive, but we can detect the whales and the dolphins and the porpoises using our array of hydrophones. And in collaboration with Dave, we put the acoustic receivers on our hydrophone moorings. So we've been detecting striped bass, Atlantic sturgeon, and several shark species. And the exciting thing is, as I said, a lot of this work has been done coastally. Our moorings go out to 60 kilometers offshore. So we're looking much further offshore and able to look at how far, not just are they going coastally, but how far are they going offshore. And we're seeing some really interesting seasonal patterns in the offshore movement of fish as well. And this work has now been funded, so we'll be doing that for another 2 years with now an array of 20 acoustic receivers. So that's very exciting. I'd say we're in a data deluge stage where this is really the analysis techniques trying to catch up with the technology. So that's a lot of what I've been doing is working with the data and trying to apply these analysis techniques to get the most out of this telemetry information. And with the acoustic telemetry, you can now even do fine scale movements, looking at very, very small scale. So it's an exciting time. So the whale study was funded by NOAA and NASA, and I give a big thank you to the Hudson River Foundation for supporting the striped bass project, the tagging work, and this analysis work. And I thank you all for listening today.
Questions? I have one. Can I start maybe? You can't get a sense of where the fish are in the water column, right, when they go by these stations.
Well, if they had a depth sensor on the tag, we'd be able to, but those are usually more expensive, and they tend to make the tag, they can be a little bit larger. I mean, you can even have accelerometers on the tags now as well, so it's usually a trade-off in cost. Would you rather have fewer tags with more sensors or more tags? And in this case, they went for more tags. So no, we don't know the exact position in the water column, unfortunately.
So I'm wondering, when you're talking about strength of the currents moving the fish out, that I think what some of the Woods Hole folks discovered afterwards was a lot of the humidity down here in the harbor wasn't the sediment moving down. It was because the stratification increased so much that the flood currents in particular were very, very strong, which I would assume as the fish were near the bottom, they would tend to be pushed more into the up the river instead of down the river if they were in the surface layers. So I was just wondering whether you sort of gave any thought to that.
Yeah, we have thought about it a little bit. Yes, because as you say, conditions can be different depending on where you are vertically. And I've concentrated very much today on talking about the horizontal movement. And yeah, I mean, with the satellite tags, a lot of those have depth sensors, so you can look at their movements vertically. But yeah, unfortunately, on these tags, we don't have the depth information.
During these events, does the level of oxygen in the water change, thus giving the incentive for these fish to change their locations?
Yes, and the fact we know some fish are able to stay suggests that it's not just getting flushed out, but there is some detection of these conditions aren't right, I don't like being here, I want to move. And the fact that they went even further south in New York suggests that that movement was perpetuated for quite some time, that they wanted to get out of there. The decline in dissolved oxygen seems to be more pronounced in the lower estuary than in the upper estuary. But yes, I mean, you see it in that graph. There was quite a rapid decline in that dissolved oxygen. Yeah, as well as the salinity and temperature. Yeah. So I'm sure, yeah, that was definitely not ideal.
Any of the tags still working?
Not of these, no. So they're tagged back in 2009, 2010, so none of those are working. But the data has been tagging more striped bass since.
Are the receivers still working though? Like for instance, the stuff that say white fox or somebody else may have tagged, are there fish still swimming around with tags that they're for striped bass?
In the harbor, right now, I'm trying to think if there are, we were lucky during the period of the study, particularly in 2011, we had very, very good receiver coverage, not only with Dave's receivers, but with Dwayne Fox's receivers as well. And so, yeah, that's obviously a key part of it, being able to maintain these receivers. So if you have the tag fish, you know where they're going. Whether they're in right now, I'm not 100% sure. But I think, Dave, been doing more tagging in this area, so there's obviously some, yeah. Yeah, and they're going to be doing some mobile tracking as well. Yeah, so that will give us finer scale information with the mobile tracking, but over a shorter period of time, so they obviously can't track them for more than a day. Oh, there you go.
Let's take some sort of communication or public education aspect of this. I know for some of the different tracking data that's available, almost in real time to the public, to help get people excited about fish or whatever species conservation. Has there been any thought for this data and make that available? And have you got to have any considerations whether that's possible, the utility of it?
Yeah,
The ownership of the data, whether it's
and that's always tricky. And so with satellite data, tag ownership is usually the person who tags the animal, and that's sort of been translated into the acoustic telemetry as well, because obviously you can put out a lot of receivers and maybe not have tagged any animals, and generally the data is considered the ownership of the person that tagged the animal. And if you detect animals on your receiver, you generally give it to those people, and you often might collaborate, but it's generally been the tag owner that's owning it. Dave has been, as I showed you, that video of him tagging is on a public YouTube and linked to his website. So anyone can go and see that. That's a public site. He also has another video that's nice, where, again, to me, that they've made a video where the receivers light up and the color lights up depending on the size of the fish. And again, that can sort of be used as a tool. So that's a really fun visualization as well. And again, that's just publicly on the on Dave's website. In terms of actually just giving the tracks, I know Dave has collaborated with a number of different people. I don't know if he's actually been contacted by schools. Is that sort of you're thinking with the outreach?
schools or other programs?
Yeah, I know. I get contacted a lot about the whale and turtle data. I don't know how much Dave's been contacted about the striped bass data, so I'm not sure. That would be a question for Dave. But generally, especially this data, which is several years old now, there's usually, a willingness and interest to see young people get excited about this kind of thing. I think it's so exciting to see these movements and to think that's a real fish. You're following a real fish. And we actually there was an outreach program with the Tagging Pacific Project called the Great Turtle Race, where those tracks I showed you, they had different companies sponsor them, like the Stephen Colbert Show sponsored one of the turtles, and so it was on his TV show, and they used it as a fundraising, and you could watch these turtles and see which one was going to win, how quickly they're going to reach Galapagos Island. So I think there's a number of creative things you could do, and I'm not sure as much of that has happened with the striped bass work, but it's certainly potential to, and try and get more people interested.
Helen, we have a question up here, and for those folks on the webinar, if you go to the right side of your screen and you want to type in a question, you can do that.
Yeah, so is one goal to predict when striped bass will go based on environmental conditions, as you did with the whales? Yes. So the habitat modeling I'm doing right now is using a similar approach to to that I used with the whales. Is that the process we go through of, say, when we reduce it to various metrics, usually things like turning angles and speed, and then we can recreate movement patterns, reconstitute, and then we want to predict. And I think what we've learned is predicting movements usually requires some understanding of the prey and or environment. It's just using movement speeds and turning angles, we can create tracks, but they're usually very unrealistic. And so we found that if we really want to predict movement, then we normally need to include prey or environment. And so often with the species we're studying, we don't have prey data, certainly not in near real time for these types of tools, and that's why environmental data that's available on that more near real time time scale is more usable. And that means then for management, it's not just a case of, oh, we've collected this data and last year this is where the fish were. For example, we can tell, okay, if you're planning, for example, dredging or something else for a certain time period, well, we expect there to be fewer striped bass in one area at a certain time of year. Hopefully they can use that information to inform their decisions.
Not sure what the first part means, but what's the cost of the tag?
What is the cost? Oh, so for the acoustic tag, you're looking at about, for the most basic one, about $350 for each tag. If you want more things, sensors included on the tag, like we took that depth and say you can even have accelerometers now, look at really fine scale movements, then you head up to more like $750 a tag. The tags that compared to satellite tags, which are more like $2,000 each, are relatively inexpensive. You also, of course, need the receivers, and those can range in price from $3,500 to $5,000, depending on whether you want an acoustic release on them to retrieve the receivers. It adds up, and then you've got the time and effort. But certainly, acoustic tags right now are one of the most inexpensive electronic tags. How many years of data would you need to have strong confidence in your predictions? Well, the approach I'm taking with the striped bass is, I was actually thinking about, because there's two approaches. Either you can hold back some of your data, so you're creating your model with a smaller data set because you're withholding some of that data to test it with, or you can use all the data and then use an independent data set to verify it, like we did with the whales. We wanted to include as much tracking information as we could, and then we used sighting data to verify the prediction. And that's sort of what I was thinking with the striped bass. It's nice to be able to use as much information as you possibly can with the tracking data to create the module, and then use, for example, survey data to verify your prediction. In terms of how many years of data do you need, I mean, ideally you want at least 2, so you can capture some interannual variation. Obviously, more would be nice, but you have to work with what you've got. So I think at least 2 gets you started. And the nice thing is, as we can make predictions in the future and more tagging per turn, you can use tagging in the future to see, is your model still predicting things well, or is it at a point where they need updating? And it's obviously with climate change, we may experience conditions we've never experienced in the past, and there may come a point at which the models need to be updated. Do we know if fish were males or females? We know how long they were. I'm trying to think if they've also had recorded if they were males or females. I don't remember seeing that. In the spreadsheet he gave me, I didn't see that. That doesn't mean he doesn't have it, but I don't remember seeing it. I just looked in relation to size. I didn't look in relation to sex.
Okay, I just would know if you could, the definition of spring storms, would that be also include when ice is formed in the river bottoms?
Yeah, so I just looked at the tropical storms Helen and Lee. You could obviously look at other events, and I mean, this approach is certainly not specifically to those events. I mean, yes, absolutely, if there's something else that you think could be affecting them, you could use this approach to look at that. Yeah. I mean, isn't it, for example, with the grey whales, we're seeing the southward migration as they move from the foraging area to the breeding area, which is a very well-known long-scale migration. They go right from Beaufort, Chukchi Sea, all the way down off Alaska, all the way down to Mexico, and we're seeing the initiation of that southward migration earlier and earlier because the ice is melting earlier. So we may well see, patterns change in response to changes in ice and in the rivers. I mean, that's obviously a very important event.
I'm just guessing, right now you've got a relatively few number of sensors and a relatively few number of fish, and the metrics you're collecting are also relatively few. But the future that you get here is you basically have animal-based sensors sensing the environment that are in some way more comprehensive than certainly the static sensors and even some of the satellite sensors. So can we imagine a future, just as you talked about the whales and the ice, where really the predominant way of, say, sensing the state of the Hudson is perhaps thousands of cooperative fish, if you call it that, right, moving through that space, measuring it each dynamically. And that is perhaps a better measure of the state than any other sensor system, at least in some ways.
Yeah, I mean, there's obviously still, in some cases where, you can have sensors off a pier or something like that when it's relatively easy to access. But yeah, I mean, one of the goals of the Tagging Pacific Predators project was animals as ocean sensors, where they're recording temperature and salinity and other things. The idea that you can have these animals collecting this information. I mean, the tags are getting cheaper, smaller, the battery power is lasting longer, all these things. I can certainly see that in the future potentially.
Well, I can see when you're going to see a price range of around $20 that your average fish shop might start selling these, and some of your more wacky fisherman persons will be putting them on and contributing science, sort of community science in this way.
Well, and one of the things that they've been developing is what they call chat tags, where tags can communicate with each other. So, for example, you can have a tag that maybe has more sensors processing inside it, but it's able to communicate with perhaps a smaller, simpler sensor. So we could say, we'd be able to detect that this fish was in proximity to this fish, and actually you can transfer information between them as well. And the idea that they sort of had that in mind with social behavior, but it also means potentially you don't need an expensive tag on every fish. You can have sort of simpler tags and cheaper tags. So I mean, as I say, the technology is really advancing quite rapidly. So we'll see. I mean, obviously you've got the issue of you saw from the video, you've got to they usually cut into the fish and put in the tag and stuff. Well, I guess, I suppose I work with sea turtles and marine mammals a lot of times. You can't do those things, but yes, potentially it becomes more accessible,
I have a couple more, maybe we can close that after where the arrow is and methods to develop.
Analyze more than a single tag species. Is it something of your interest? Oh, yeah, absolutely. I mean, it's really interesting because more species are getting tagged. I mean, we have different life stages getting tagged now as well, mostly in the past. Has methods been developed to analyze more than a single tagged species? I mean, a lot of the times we're talking about a single species. So in the Tagging Pacific Predators project, a paper came out by Barbara Block in Nature in which they did analyze all the species I showed in that map. So it's certainly of interest to look at it on a multi-species perspective, ecosystem-based approaches. And I think as we're tagging more species, then the capability to do that is certainly increasing. I mean, it's been interesting, even just looking at the detections we've had in the Maryland wind energy area. We've got striped bass, sturgeon, and then shark species. But then as someone was mentioning, I mean, a tag, one of the more conventional tags was found inside a dolphin. And as I say, we have hydrophones out there detecting dolphins as well. So you can start thinking about predator-prey interaction, which will be very exciting. I would say so far there are relatively few studies that have been multi-species with tracking data, but I certainly think it will increase in the future.
Yeah, you mentioned the chat tags with fish can talk to another fish. What is the mechanism for that communication between tags?
I'm trying to think exactly. I haven't actually used any of them, but I was talking to a few scientists who put it on shark species. Now, the difficult thing with it is it doesn't give you location specifically. So you'll have a time when they communicated, and I'm trying to think of how that communication actually worked. But because they weren't at the surface, they didn't have a geographic location for when did that occur, when did that interaction occur. So yeah, I'm trying to think. I mean, I think it would have to be some kind of acoustic signal to work underwater, because they weren't at the surface, so I think it must be acoustic.
And a secondary question. I noticed on one of your earlier slides, you had acoustic hits out in the ocean, in an area, say, 20 miles south of Fire Island, or what we call the Ambrose Tower area. So do you have acoustic receivers in the ocean near the Ambrose area?
Well, and of course, it might not necessarily be our receivers. I mean, through the telemetry network, and there's many, I'm not sure how many groups it is right now, but lots of different groups that will contribute their receiver data and share it. And also, those aren't static in the sense they might have been there during that time period, but then, if the project isn't funded anymore, they get retrieved. So the network of receivers is dynamic because it's project specific. As far as I'm aware, I'm not sure if any are really long-term funded, so most of these are sort of 1-2 year projects. So yeah, it's difficult to get long-term funding.
I think we could take these last maybe 3 questions.
Did each tag include age class at the beginning of the study? I looked at the length of the animal, which ranged from, I think it was around 480 millimeters up to over 750 millimeters. I'm not exactly sure what age classes they correspond to. I just looked at length. Dave would be a better one to ask about that. Is the data going to be shared after publication? So the study that I showed you looking at those tropical storms has been published in the journal called Scientific Reports, which is part of the Nature Publishing Group, and it is open access. So even if you just Google Helen Bailey strike bass, it should pop up with the paper. You don't need any subscription to the journal. It's freely available, and you can download that PDF. The data sharing, I know Dave has shared it, I think, with certain groups, so if there's certainly interest in collaborating, then get in touch with Dave and Dave or I. I think there's certainly interest in seeing, as much use of the data as possible, and if people have other ideas of how it could be used or put together with other information, that would certainly be of interest.
And just on the second to the last question, Wayne Richards with New York State Department of Environmental Conservation.
Okay, we collect striped bass from just below Victoria Dam each fall for PCB analysis. Excellent. We attained our target of 10 fish on 21st of September 2011, suggesting that some fish either stay well upstream or return very quickly. Any thoughts on this? Yes, as I say, I mean, the ones that we saw tag, like two were in the harbour and one was just sort of in the northern part of the harbour. And given that they were able to maintain their position, as they indicate to me, it was not all striped bass that moved out, that they were able to maintain the position. As they, we certainly saw those exploratory movements, so the fact they were able to return, we did see that behavior. I think, and we do see this in a lot of other species as well, if animals are displaced or avoid something for some reason, they often do try and go back, whether there is this sort of innate, this is where I want to be, so even if they do move out of the area, they just try and get back to it when the conditions are suitable again. So say, in some ways, it's potentially, some of the animals did stay in the more coastal environment, which might sort of more longer-term impact, but others didn't. And so particularly, I think the upper estuary contingent, who wanted to be further upriver, they wanted to get back. So that was shorter-term impact in that sense. As I say, if storms just keep coming, then would we see longer-term impact? Shall I do the last one as well?
Why don't you do the last one? Worrying about.
I'm trying to remember which slide 40 is. You indicated the fish very quickly to the harbour after the second storm in 2011. In 2010, 15 to missed or receded along the Hudson. So how do we know they true speed of exiting the Hudson? So I should just say, obviously, we have a case design, but it clearly isn't perfect. Because, yes, they shouldn't really have this, they should be going to, we've already got receivers, and we had receivers, as you can see from this period. Why didn't we get detection? Even though technically we should have had a detection range, that meant they shouldn't have been able to go through, there were some occasions when that happened. And so, as I said, sometimes it is an assumption. And the speed that I've calculated here is just an average. So assuming, from this location to this location, given that distance and given the time, this would have been their average speed. So potentially, well, we know, they weren't detected at this receiver anymore, but again, if they move out of that detection range, so that there is some uncertainty. And one of the things I've been thinking about is the state-based model technique that we used for the satellite tracking. Could we modify it for acoustic telemetry to try and take that uncertainty into account? Use information about their previous movements like this to help inform how would they have moved through here. In this case, I took the simpler approach of just assuming they moved from this position to this position over this time period, is that we could move to much more complex Bayesian state-based model techniques where we do incorporate uncertainty in it to come up with better estimates.
One more.
Yeah, I was just curious that endgame was the model was constructed with whales, so you can input environmental data and then output, predict where the whales are going to be. What's the real-time environmental data that you can be inputting into that?
Right, so that's actually the part I've been working on right now, because with this study, I didn't need real-time information. So what I was looking for was just what was the best information available in 2010 and 2011. And initially, I was going to just take that information to create the model. But then, as you say, if you want to make it into a near real-time tool, then you need environmental data that's going to be available fairly readily, which means you want to pick variables that are relatively easily measured, that don't take a lot of processing, that are routinely recorded. Temperature, obviously, is usually a great one for that. But it did make me search much harder to look at what sources were collecting data right now, and did they have data before. And unfortunately, what I was finding, and there's a lot of cases, the stations where I had data for the time period of the tracking, they no longer were doing it right now. And so what I was doing is essentially kind of calibration. So if I take data from one source and then I kind of calibrate it, can I work out a correction factor effectively for the near real-time data? But that was definitely an important lesson learned with the whales. That you don't want to create your model on one set of environmental data and then just use the new data, because there can be differences just through different instrumentation and different ways that data is processed. So yeah, that's what I'm working on right now, making sure we have that continuity.
Well, thank you, Helen. And just another reminder,